Организационного комитета поприветствовать вас, участников IV Международной конференции «Информационные технологии и нанотехнологии». Organizing committee, let me welcome you to the participants of the fourth International Conference Information Technology and Nanotechnology. Мне бы хотелось пожелать нам всем хорошего недели. Хотелось бы надеяться на то, что результаты обсуждения на этой конференции будут плодотворными. So we hope that your work during these several days will be fruitful and you will get enough fine results during the discussions on this conference. И сначала мне бы хотелось для открытия конференции передать слово первому проректору по науке и инновациям Самарского университета Андрею Брониславовичу Прокофьеву. So for the opening of the conference, let me introduce you the Vice Rector, first Vice Rector, Rector on Information and Science of Samara University, Андрей Прокофьев.
Доброе утро, уважаемые друзья, коллеги, сотрудники и гости нашего университета. Позвольте мне от имени ректора, который сейчас в командировке, поприветствовать всех присутствующих здесь. Как вот Александр Викторович сказал, это уже 4-я конференция. И вот опыт предыдущих конференций, я думаю, и этой показывает, что вот та инициатива, которую мы несколько лет назад проявили в учреждении этой конференции, она оказалась очень такой плодотворной и очень перспективной. И действительно, тематику, если мы посмотрим конференции, она охватывает все стороны нашей жизни, которые проходят в таком информационном пространстве. Это и оптические вычисления, за которыми говорят будущее вычислительные техники, и близкая нашему университету тематика анализа данных дистанционного зондирования Земли, многие из которых получаются сейчас благодаря гиперспектральной съемке, которая требует особого обработки, таких больших объемов обработки информации, и отсюда и большие данные, и многие другие темы, которые вот сегодня, это темы сегодняшнего дня, темы будущего, темы цифровой экономики, которые строят все современное человечество. Присоединяясь к Александру Викторовичу, я надеюсь, что вы не только обменяетесь своим опытом, обменяетесь научными достижениями, но и найдете время посмотреть наш чудесный город. Погода как раз с сегодняшнего дня к нашей конференции, к вашему приезду установилась очень хорошая, солнечная. И это, я надеюсь, позволит вам получить удовольствие как от научной, так и от культурной компоненты конференции. Всего самого хорошего, плодотворной работы. Спасибо.
И также для приветствия хотелось бы пригласить заместителя председателя правительства Самарской области, руководителя департамента информационных технологий и связи Самарской области Казарина Станислава Валерьевича. Also for welcome speech, let me introduce you the vice head of the government of Samara region, the the head of the Department of Information Technologies of Samara region, Казарин Станислав.
Добрый день, уважаемые участники конференции. Позвольте от главы региона Дмитрия Ильича Азарова поприветствовать вас здесь, в стенах нашего национального университета. И весь блок правительства, который отвечает за научно-техническую политику на регионе. Я очень рассчитываю на то, что сегодня будут замечательные доклады, будут замечательные открытия, будут замечательное общение. И, конечно же, будет замечательная культурная программа в городе, который активно готовится принимать чемпионат мира по футболу в июне-июле 2018 года. Действительно, мы очень рассчитываем на то, что современные университеты, которые активно реформируются и движутся по модели университета 3.0, занимаются не только научными исследованиями и образованием, но и коммерциализацией своих разработок. Рассчитываю, что здесь сегодня будет заключено большое количество соглашений друг с другом, которые позволят капитализировать ваши решения, ваши открытия, ваши достижения на очень высоком международном уровне. Успешной работы всем. Спасибо.
Итак, мы можем считать конференцию официально открытой. И сейчас мы тогда не будем откладывать, начнем нашу пленарную секцию. So, let's state that the conference is now officially open, and thus we can begin our plenary section. And let me introduce you the chairman of the first plenary section, the Michael Sobolevsky, who is the Doctor of Science, and he now working at the Polish-Japanese Academy of Information Technology. He is also a representative of the Institute of Computer Science of Polish Academy of Sciences from Warsaw, Poland. So please, if you can, we may begin our plenary section. Thank you.
Yeah.
And the first speaker is Professor Dieter Wimberg from the Institute of Solid-State Physics, Technical University Berlin, Germany. And his presentation is on the topic I ask Professor Wimberg to introduce himself. I can give you my microphone. It works. Does it work? No. Okay, you can use mine.
The rest is going to be in English. Although I'm coming to Soviet Union and to Russia since many, many years, I'm since almost 20 years honorary member of the Joffe Institute of the Russian Academy of Sciences, and I'm a member of Russian Academy of Sciences. I think that's more or less all you need to know about me. And I'm working on a vertically integrated research approach based on materials, on new materials like nanostructures, which we make ourselves or fabricate in cooperation with the Joffe Institute, but also with Siberian Academy of Sciences in Novosibirsk, where I'm going to regularly. And then we test these materials, characterize them, photoluminescence, and we make devices out of it in clean room. And today I will report you on essentially the beginning of the start of work on quantum dots. Why did it happen? And try to answer the question with 2 examples. Is it useful? Now, a quantum dot is a semiconductor cluster consisting of several thousand of atoms, but electronically it resembles an atom in a dielectric cage and not a semiconductor. And you will learn in a second why it is closer to an atom than to a semiconductor. Now first we need to define size and morphology of coherent quantum dots. If you hear cluster, you think, okay, something disordered. A quantum dot is something very well ordered. It's inserted in a semiconductor material and has no broken bonds in any direction. But it must obey a number of geometrical boundary conditions. Number 1 is the lateral extension in all 3 directions of space must be smaller than the de Broglie wavelengths of the charge carrier. So that is for the physics students, right? They should know what de Broglie wavelength is. However, it should be not too small, otherwise there is no bound state inside. You can have 500 atoms, no bound state inside. And it should be not too large because you want to have the energy difference between sublevels, electronic sublevels at room temperature larger than kT, and kT is 26 millivolt. So this is a picture, a high voltage blend view picture, 1 million electron volts of an indium arsenide quantum dots embedded in gallium arsenide. Yeah, it looks like it's a little kind of not very healthy surface, but it's just the opposite. It started many years ago, 1986, with a thesis of a Japanese scientist working at the Tokyo Institute of Technology, Mr. Asada. And he did some calculations. He calculated the gain and the threshold current density for a number of material. For one material, gallium indium arsenide on indium phosphide, that is a material which is today used for long wavelength lasers, for the internet, for the intercontinental internet at 1.55 micrometer. And he calculated that the gain increases if you go from bulk material, indium gallium arsenide, over quantum wells, quantum virus to quantum dot. It increases from 30 centimeter reciprocal centimeters to about 8 times 10 to the third, 8,000. Yeah, so it's an increase of about 2 orders of magnitude. Then he calculated for gallium arsenide embedded in gallium aluminum arsenide the threshold current density. And you see from 3-dimensional down to 0-dimensional, the threshold current density decreases. Yeah? And that's, of course, a very important number for any light-emitting device. The transition from spontaneous emission to stimulated emission is the most important number, because up to the break point here, where stimulated emission starts, all the electric current which is injected, most of the electric current which is injected is just creating heat. And only here, starting here, and this is a double logarithmic scale, only here you are at a moment of time when any additional electron-hole pair which is injected can leave the device as light. From here on you might have, if you're really good, and that is what we have with quantum dot lasers, from here on, you have 100% slope efficiency. So these are very important predictions in the 80s, so many years ago, almost 40 years ago. And they triggered enormous amounts of device work all over the world, which never led to any 300 Kelvin device. The best device, which was published 8 years later in 1994 from the same institute, was a laser pulsed at 77 K, that was liquid nitrogen temperature, having a a threshold current density of 10 kiloamps per square centimeter. That was just enough to take the IV characteristic, and then it died. Yeah? So that was very disappointing because many companies had invested a lot of money. Now, the assumptions which were put into all that work, into the theoretical work, was you should use lattice-matched heterostructures. That is, most materials which you use today, most 3,5 materials or 2,6 materials are indeed lattice-matched, but not all. The assumption was infinite barriers, something like that doesn't exist in physics. One electron in one bound hole level only, and you have an equilibrium carrier distribution, which means a Fermi distribution. This proved to be an unsuccessful technology. This is just incorrect. That is incorrect, and that is partly incorrect. Nevertheless, people didn't realize all that, what is written in red here. It triggered an enormous amount of work. Now let's switch to physical chemistry. In physical chemistry, we have to consider the surface growth modes. And we have to consider strain in non-lattice matched heterostructures now, which drives the quantum dot formation. So we have two classical growth modes. The van der Merwe growth mode, which is based on large surface energy. Then you get a thin wetting layer if you deposit a second material on top of a first material. Then you get layer by layer growth. That is the Frank van der Merwe growth. That second growth mode, which is if you have large strain film energy, you result in three-dimensional clusters. That was discovered by Professor Vollmer, professor of physical chemistry actually at Technical University in Berlin before the Second World War, and his co-worker Weber. Then, end of the 30s, a Bulgarian scientist, Ivan Stransky, found out there is a hybrid of both. You start with a thin wetting layer, and after that you have a first order phase transformation on the surface, and you get clusters which can be coherent clusters. The first results of this work were presented in 1938 at a meeting of the Physical Society of Vienna, which was the first before the Austrian Academy of Sciences came into existence. Yeah, 38. Stransky later on moved to Germany, always Bulgarian, and became professor at Technical University of Berlin after Second World War, and was the successor of Vollmer, and became president of Technical University in 1952, still having a Bulgarian passport. I think this is a very nice historical side mode of science history. Now we grow quantum dots, for example, indium gallium arsenide and gallium arsenide, where you have 7% mismatch of the lattices, by just putting one or two monolayers of indium arsenide or indium gallium arsenide on top of a very clean gallium arsenide surface. And what you discover then you discover square-shaped quantum dot base, which is, this is a picture again, high voltage transmission electron microscopy. It's square-shaped. We have self-similarity because the underlying mechanism for the growth of such structures is self-organization. The edges are always parallel to 0, 0, 1. Sometimes you have ordering along 0, 0, 1. And all the old paradigms have to be now replaced. The new paradigm is, if you talk about nanostructures, they must consist of material with larger different lattice constant in order to initiate the strain-driven. Strain is the most important, self-organization. Then free carriers and excitons are delocalized in our space. This is classical solid-state theory. Yeah? So delocalized, you have wave functions, Wannier functions, which are going across the whole material. And wave energy as a function of wave vector is continuous. Wave vector and energy are conserved, and the gap is a function of chemical composition. And at higher densities, the excitons are screened, and solely free electron-to-hole recombination exists, That's what you see when you emit light from diodes, from LEDs or from lasers. And finally, you have a variation of index of refraction with carrier density. In nanostructures, everything has to be reversed. First, all carriers are strongly localized in a volume which is 10 to the third, approximately 10 to the third cube nanometer. The energies of carriers are discrete delta functions. Yeah? So there is not an energy of momentum vector dependence. The carriers have no well-defined wave vector. There is no wave vector conservation and no recombination bottling. That is a function of this here. This is very simply what everything has learned at the beginning of his studies, Heisenberg's uncertainty relation. If something is strongly localized in R space, it's completely delocalized in K space. Yeah? So these are fundamentals of quantum physics 1926. Finally, the recombination and gain is always excitonic or biexcitonic, which leads to a large enhancement of the oscillator strength because you have this strong overlap of electron and hole. Why is that? Now, the carriers, the electrons and the holes, they are enclosed in the quantum dots. They cannot escape each other, which means they see always Coulomb interaction. Yeah? That means everything is excitonic. And finally, the index of refraction of the waveguide does not depend on gain of quantum dots. That is a little more complex to understand, and if you have questions, I will explain it a little later. Now, zero-dimensional systems are compared here now to 3, 2, and 1-dimensional systems. The impact of dimensionality, yeah, is kind of shown here. 3D, quantum wells, quantum virus, and quantum dots, and here you see the Hamilton operator and the momentum operator commute, and here they don't commute anymore. And what you see here now from left to right is, first of all, you see energy of wave vector diagram. Here is I see a square root. Then you see a step function for quantum wells. And here for quantum dots, we see delta functions. Now, in reality, you have, of course, always some inhomogeneous broadening in nature, which will influence the density of states, such that, for example, the step function density of states is kind of smoothed out, but it does not influence the quantum dots. The density of states, whether the interface between the surrounding matrix and the quantum dots is steep or not, it doesn't matter, it's a delta function. And now you populate it thermally, and you find that finally, if you populate them thermally with carriers, they're looking very much the same, except it's getting narrower if you go from 3D to 1D. Here, it's still a delta function, so its emission is delta function-like with a small Lorentzian broadening as a function of the finite lifetime of the charge carriers in the quantum dots. And here are some wave functions which we calculated based on 8-band K to P theory. And you see that you have energy level structures. And what is most important for electron and hole levels is that all these levels show a twofold degeneracy of the energy states. That means, result, that the energy level structure of a quantum dot is simpler than a hydrogen atom. In a hydrogen atom, you have sp, d states, etc., etc. Here, you have only twofold degeneracy, right? And the wave function, the fundamental, ground state wave function looks still for the electron a little similar to a S-state hydrogen. That is px and py states. These look a little similar, but it's split here by a certain value. The whole wave functions show no similarity anymore with any atomic wave functions. Now, do we have applications for these? This was a very short excursion to the fundamentals. Novel photonic devices, and I will talk briefly about single and entangled qubits for quantum cryptography. And I present you a single quantum dot LED, which is based on one quantum dot. And then I will talk about energy efficient devices, which are useful for local area networks, metropolitan area networks, I will talk about lasers based on inhomogeneous distribution of many quantum dots. And if somebody asks, have quantum dots arrived in applications? Of course. Each of you has quantum dot-based devices. Because the green LEDs and lasers, which you have today, there are quantum dots inside, otherwise a strongly dislocated material would not emit light. Yeah? And that is actually known since 20 years almost, since the first work of Nakamura, who was working on this subject. Now let's start with cybersecurity. I was reading when I was flying to New York a few years ago, 2012, in New York Times, cyber attack on Saudi firm disquiets United States. And there was a cyber attack on Aramco, and they had to close their production, which was a loss of about 100 million US dollars in one day. Yeah? More recently, we had, during the elections in the United States, there were cyber attacks on email accounts of Democrats, which disquiets still as a popular voice, at least in the United States, and strains a little the political relationship between the United States and some other countries. Now, what can you do? The classical cryptography started with Enigma, which was a decryption machine developed by the British Secret Service in the Second World War. And when Alice talks to Bob, there can be an eavesdropper, and that is something we would like to avoid. And the message, my message here in the next 5 minutes is that single photon sources, emitters of qubits, quantum bits, will play a decisive role in physical layer security. And the basics are the following. Now, information science. Location and momentum cannot be independently determined. A measurement perturbs the system. This is all Heisenberg. Qubits cannot be duplicated. The engineers reinvented that and called it now non-cloning theorem. It's a paper came out in IEEE journal recalling it a non-cloning theorem, Heisenberg's uncertainty law. Very interesting. The measurement of the polarization state of a single photon disturbs the polarization. So quantum mechanics enables secure transmission of data. That is the message. Now, our objective is electrically triggered single photon sources with polarized single photons or entangled photon pairs. And the realization can be done in the following way. Ground state of the quantum dot, where I just have shown you the wave functions, right? You remember these funny wave functions? Now we have one electron and one hole in one quantum dot. These are form an exciton. Now we have a fine structure splitting, which is caused by the piezoelectricity, which splits the fundamental states with the fine structure splitting. The difference is that. And as a function of that, you have a polarized one photon emission. When this one electron hole pair recombines, and everything goes into an empty state. So you have a 1 or a 0. And remember, I mentioned we can put a maximum of 2 charge carriers inside a quantum dot. Now, what means 2 charge carriers? 2 electrons and 2 holes? That's the excitonic molecule, like hydrogen molecule. Excitonic molecule. And you can have, of course, a recombination cascade. Molecule, single exciton, 0. And both transitions are polarized. And if the first one is px polarized, the second one is also px polarized. Yeah? And the states can be entangled. And what we try to do now is fabricate such a device where you have one quantum dot inside, and you have some mirror here, yeah? A Purcell cavity, large fine structure splitting, a micro cavity, and then you have a single photon source with polarized emission. So this is a challenge for students, but Students are typically pretty ambitious and they made it. Here is such a device. You make a layer of very strongly diluted single quantum dots, and then you make a trick which we learned from fabricating surface emitting lasers. We fabricate oxide apertures. What is oxide aperture? It's aluminum arsenide which is oxidized in vapor, in water vapor, such that it transforms to aluminum oxide. What is aluminum oxide? Sapphire. A strong insulator, suddenly you have, instead of a semiconductor, you have an insulator. The insulator, first of all, channels the current, and second, of course, guides the light. Yeah? This is a very, very good trick, and that was the basis that we could really fabricate now such a device. And this is already a high-frequency layout where we used ground signal ground layout for enable high-frequency operation. And you see here, it should move on top of each other. So you see here's the light coming out at 850 nanometers of one single photon. Next was resonant cavity LED. We just introduced now DBRs here. 2 stacks of DBRs. And now we have quantum dots in a gallium arsenide cavity, density of 10 to the 8 per square centimeter. And if you're lucky, you have a quantum dot below this aperture. And we can then pump electrically one single quantum dot. It's a PIN junction, very simple. You have here the P contact, here is the N contact, yeah? And we have a micro cavity, and the cavity must be, of course, in resonance with the luminescence, but all that can be done. And here is the result, a completely empty spectrum, completely empty, weak pumping. You see a recombination of one single exciton inside. That is, what you see here is a qubit. And if you look a little more in detail with a high resolution spectrometer, you see that indeed, as predicted by our theoretical calculations, the light emission is polarized. Half of it is 1 minus 0, 1 minus 1, 0, and 1, 1, 0 along the axis, the fundamental axis of the 3-5 semiconductor. And the efficiency already was pretty good. About 20% of photons per injected electron-hole pairs. Now, the problem is, of course, sometimes a quantum dot is below the oxide aperture, sometimes not. In about 98% of cases not. So the student who did that work had to search around 5,000 of such devices we had on one wafer until he found 10. Where really the quantum dot was below. So this was an idea which could be improved. Now we did the opposite. We were growing the DBR, fabricating the aluminum oxide, and then did the modeling and found out that on top of such an aperture, you have a strained area, and indium atoms are larger than gallium, so they move automatically towards this hole. Yeah? And suddenly we found a possibility to control the quantum dot position, which is essential for mass production. And you can do the same at 300 Kelvin actually, making gallium nitride based single photon emitters. And what you see here now is the so-called the result of a Hanbury-Brown twist set up, which tells you that really the second order correlation function goes to 0 at the point when the quantum dot, the qubit is emitted. And here you see now the picture of the device, and you see that the light exactly comes out from the center of the device. Yeah? This is a really operating single qubit emitter, a PIN junction. no atomic physics, no diamond, which cannot be where you cannot make P and N contacts. Yeah? And all these emitters we can modulate up to presently 1 gigahertz or 2 gigabit per second, which is quite nice, which is useful for making now keys. At this point, I will switch the subject from one quantum dot to many, 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 and switch to local area networks, metropolitan area networks, and access networks. And I will show you that quantum dot lasers present the basis for green, which means energy efficient lasers. Today only lasers, not amplifiers, using the inhomogeneous distribution of many quantum dots. And I show you a little higher modulation rates, and the goal is now several terabit per second with one single energy efficient device. And the basis is now the fact that never two quantum dots are really identical. And at the beginning, when we started with this work, some people said it's not useful. How is it? It would be better if you make all quantum dots the same. If you have, let's say, 1 million quantum dots in your device, it should be all the same. That person had never heard about the third law of thermodynamics, about entropy. Yeah? It's just not possible. There's no way. Yeah? And I could go into details. We did a lot of modeling of the growth, what the influence is. And that is actually very helpful, as we'll see in a second, because if you want to create lasers which emit short pulses, it's very helpful that they are inhomogeneous distributed, the quantum dots. Now, we have in information technology, we have continuously emerging applications. And one of the examples is Netflix. I don't know, is somebody here receiving Netflix, watching Netflix? One only. Well, if I ask something like, I was just coming back from Singapore, including all professors, everybody was raising his hand. Yeah? My children, I have children, they don't watch TV anymore, they're watching Netflix. Yeah? Netflix is a service where you can download movies very fast, and that is responsible for 1/3 already of the internet traffic in the United States. Yeah? And you have here global traffic increase is about 60% per year. In the last few years, controlled by these consumer applications, not by applications in industry. It's all you who are driving the internet use, driving it up. 60% per year, which means 100 times in 10 years increase, or 10,000 times in 20 years. And if you look now to the detailed supercomputer performance, microprocessor performance, storage, etc., you see essentially here you have a so-called cumulated and annual growth rate of about 60% per year. If you go, however, to routers interface speed, transport interface speed, WDM capacity, you see that here we have only 20%. Yeah, 20% increase of capacity. That means within 5 years there is a gap of a factor of 4 between the speed, and in 10 years a factor of 17 between the optics and the electronics. So we have to do something about that. Now, 2 facts about Internet protocol itself. The Internet traffic doubles nearly every 36 months. Now look at there are 3 numbers here. Total, okay, increases, we know that, but until 2014, long haul, that means intercontinental traffic, was the same, used up the same capacity as metro. And now metro has taken over. The intercontinental develops much less speed, And the metro is the one where you use all kinds of WhatsApp or what is the one in Russia? Telegram, yeah. That's the one which is kind of driving the needs for capacity. Yeah. And here are some numbers. Everybody, each person uses up 17 gigabyte per person and month in 2017. The world network power consumption this is a number from 2015, was 5% of total power consumption worldwide. At that time was 6% today, the latest data, 9% of the total power consumption. Yeah? And 2020, 8.5 times more than today without improvement. And next, the last prediction, which is not on this slide, 2023. 2023, there is a crossover. The internet will consume the complete power production in a country, in the United States, let's say. Yeah? Is this realistic? No, it will not happen. Something has to be done. There can be something done restricting the use. And the other possibility is, takes 5 more minutes or so. Yeah? Restricting the use or having novel devices, which are increase the data rate, but at the same time, because you need to increase the data rate, because you're using more and more, but reduce the power consumption. And each bit, every information bit, spends part of its life as an optical photon somewhere in this complex network. And we do know that in the meantime, our famous friend Facebook, yeah, has installed its own cable going from New York over to Ireland because they don't want to use the classical cable of the cable providers anymore. They have a high-speed cable for using Facebook. Now, a network, semiconductor network consists essentially of only 3 elements. Fibers, which is passive, lasers, which are transmitters, amplifiers, and receivers. And I'm going to talk about the transmitters now. You want to have sub-picosecond pulse widths in order finally to transmit terabits. You want to have high repetition rates, tens of gigahertz, if possible terahertz. Repetition rate tuning, low pulse timing jitter, temperature-independent operation, and you want to create clock signals. Clock signals is just frequency comps, yeah, like my finger. It's a clock signal. And the resolution are mode-locked lasers based on quantum dots. And the same can be figured out for amplifiers, which is not the subject of my talk today. And what I show here is a quantum dot laser. You have now, you're stacking now, let's say 10 layers of such quantum dots, put it in a waveguide, yeah? Then you have an active laser structure, do a little tricks about doping levels and so on and so on. And what you find out, it's a record low threshold current of all lasers which exist. It has almost temperature independent up to 75 degrees and a number of radio frequency possibilities. And that shows you the historic picture of threshold current density of semiconductor lasers or green photonics, starting with the work of George Ivanovich at Joffe Institute in St. Petersburg, who made the first double heterostructure lasers, then later on quantum well laser. Then the quantum well started with really the development of Rusty Pui at the University of Urbana, Illinois, Wang Zheng at Bell Labs, again Alferov and some Bell Labs people. And we started with the first quantum dot laser, a student of mine, Niels Kirchstetter, who is now CEO of a laser company. That was in 1994. And we're down here now at 6 amps per square centimeter per quantum dot layer for room temperature quantum dot lasers. Yeah? So that is green photonics, energy efficient photonics. Why? I repeat, you cross the border between spontaneous and stimulated emission at a very, very low power level. That's most important. Now there are a few other advantages, and I want to focus only on this lower part here. You have an inhomogeneously broadened spectrum because you have a distribution of quantum dots. And if you take then fundamental rule in this kind of applied optics is the pulse width in time is a Fourier transform of the line shape. Very simple. So the broader the line shape, the narrower the pulse width. Very simple. It's a fundamental rule which is actually known since end of last century. Of 19th century. Okay? So the more modes can be locked and picosecond pulses are visible. And here you see a device which we have developed, which is already in a house, and it's marketed by FNICS. What is a mode-locked laser? It's very simple, very, very simple. You have a gain section, yeah? It's positively biased, and then you have a monolithically integrated central absorber, which has this absorber bias, and we have a defined phase relation between longitudinal modes and a pulse comb is emitted. So this is very, very simple. So we have here pulse widths ranging from 2 to 9 picoseconds, and eliminating the chirp, you can come down to 600 femtoseconds for optimized gain absorber length ratio. And output power, several tens of milliwatt, typically 50 milliwatt. Yeah? Repetition rates up to 87 gigahertz. Now, our goal was terahertz. So, how can I go to terahertz? I will skip a few slides and show you how we can go to terahertz. First of all, we take a 40 gigahertz mode-locked laser, yeah, which emits such a frequency comp. Then we combine it with a Mach 10 modulator later, and we do 2 times the same. Then we have already 80 gigabit per second. Yeah, this is a time scale. You see here so-called open eyes, and that is a multiplexer with clock recovery. Now, second is, I was only talking about intensity modulation. Now, each electromagnetic wave has not only intensity, which can be modulated, but also a wavelength and a phase. So you can do, for example, phase modulation in addition, and you can superimpose wavelengths. Yeah? And these are the trends in data transmission. You use so-called advanced modulation format. That means you double or triple or quadruple the bit rate at a given symbol rate. Yeah? You have in each baud, let's say, 2 bits or 4 bits, etc., etc. And one of them is so-called differential quadrature phase shift keying. Sounds horrible, yeah? It took me a long time to remember, if I can't read it, what it means. What you essentially use is you modulate also the phase, yeah? And then you can come already superimpose now phase modulation, and you come to 160 gigabit per second, for example. Oh. You can also use the absorbed light, which is here, creating frequency comps in the electrical domain. Oops, and some slide is missing. Now we are superimposing 4 wavelengths at 160. I don't understand. Some slides are missing. Anyway. If you look at the spectra of a mode-locked laser, then the spectrum is comprised of 40 different lines, all of the same height. That means if you separate these lines, you get 40 times 160 gigabit, 40 times 160 gigabit, which is 6.4 terabit per second, and that is actually on what we're working on right now. We're working on this a complete optical module which will supply, based on one single quantum dot laser, which will supply us with 6.4 terabit per second signals. Thank you very much for your attention.
Hello. Oh, I think we got it.
No, I think
He has already given me one.
Oh, okay.
We are coming.
Present it. I will present. It is working, but not properly. Can you check it? I thank to Professor Yamikov and Professor Pavliev for inviting me for this conference. It is the first time in Samara, of course in Russia also, and it was good and I feel better. So my topic is little bit changed. It is now in more generalized. It is the graphene, a wonderful material for its properties and applications. Properties and applications will discuss and limited only 2 applications. So I will go on. Myself, Professor S.S. Islam, I am the director of the Nano Center for Nanotechnology, that is in New Delhi, and its name is Jamia Milli Islamia. It is a simply Arabic name, but in English we say it is a Islamic National University. The concept of the name of the Islamic, it came like this. When in the before pre-independence there was a movement in New Delhi that we should have a system, the English education system. It was just against British rule that time. They want to simply oppose this British education system and establish our own. So it is our father figure, the father of nation, Mahatma Gandhi, and some intellectuals in the northern regions, and they belong to the Muslim communities. They are freedom fighters. So they have joined together and established this university. Now this university is simply a national university. There is no kind of secular university, and everybody can come and access all over the world. People are coming from Europe, people are coming from the African mostly, and some Arabian countries. Even in the Southeast people, they are also coming to study here. At present, we have regular students, 3,000 students plus, and we have 260 around courses are running in this university. Sacred river in India. So it is one of this river that is called Yamuna, and the university is located on the bank, and there are so many historic places just surrounding this university. This is the war memorial. It was built just after independence.